Now we have to calculate the bending moment at A, because as you know this is the fixed support actually, so that's why that will take a moment. Okay, as there is an internal hinge at this point B, no moment will be transferred from this area to this, so that's why we have to consider this only section. Okay, so we have to consider only from A to B. So how much bending moment it will raise this point A is nothing but we have to take moment at point A. So how it is like that, bending moment point A. Okay, so consider clockwise positive and anti-clockwise at negative. So find out bending moment at A. We will 10 into 2. Okay, 10 clockwise direction, that is positive, plus 5 kilonewton per meter load is there, so it is all over the length, that is 4 meter length, 5 into 4. Okay, multiplied by 2. Okay, 20 plus 40, that is nothing but bending moment at A will be 60 kilonewton meter. Okay, so this is how there will be the bending moment. Okay, so this is rotating in this direction, so the resistance will be in anti-clockwise direction, that is nothing but 60 kilonewton meter is the bending moment at point this A. Okay, so this is the 60 kilonewton meter is nothing but this reaction. So vertical reaction is 7 kilonewton, horizontal reaction is 30 kilonewton, and moment resistance is 60 kilonewton at point A, and at C 60 kilonewton is a vertical reaction. Okay, so now we will draw the shear force and bending moment diagram. So first of all, let us draw axial force diagram, AFD. Okay, AFD, calculation for AFD. So how we will draw is that there is an axial force. If you consider, uh, then there is only one vertical force, that is nothing but this 7 kilonewton, isn't it? For a member BA, we consider for member BA. If we consider member BA like this, okay, there is vertical reaction at this point, nothing but 7 kilonewton. That's why definitely there will be a one vertical reaction like this, that is nothing but this 7 kilonewton. So axial force diagram for this AB will be only like this, 7 kilonewton, like this. Okay, for member BC there is no any axial load acting, there is no any inclined load, so that's why there will be not any type of what we can say, that there will be not any kind of axial force diagram. Now second point is calculation for SFD. Okay, so for that what we have to do is nothing but shear force at A. Okay, shear force at A left will be 0, shear force at A right will be nothing but 30 kilonewton, which is in upward direction. We know the sign convention like this, we consider it as positive and this will be considered as negative. Okay, so this is in upward direction towards the left of the section, so that's why it will be considered as a positive. Then shear force at D left, left side of a D, not right side of a D left, that will be 30 minus, there is a 5 kilonewton load on over 2 meter length of this structure, therefore 30 minus 5 into 2, that is 10, that will another number 20 kilonewton. Okay, so this is like this. So shear force at D left is 20 kilonewton. Then shear force at D right will be 20 minus this 10, that will be nothing but equal to 10 kilonewton load. So how this is how we take d left and d right, because once we wanted to consider this 10 kilonewton load. When we consider d left, we consider only UDL, we do not consider this 10 kilonewton load. Okay, this 10 kilonewton load was not considered when I calculate shear force at d left. But when took d right, then what we do is we consider this 10 kilonewton force. That is only the difference we make by taking the section. When I say shear force at d left, I take section at this, okay, and I look in leftward direction or downward direction, and I consider this reaction, I consider this UDL, but I do not consider this 10 kilonewton force. When I say shear force at d right, then I consider the section at this point and I look in downward direction and I consider 10 kilonewton force. That is the only difference I make when I say shear force at d left and shear force at d right, because once I want to consider the cause and once I want to consider the force, and then I do not want to consider force, like that this difference is only there. Then shear force at B, there is no any load at point B, so that's why we can consider at shear force at B only, that is 10 kilonewton is there minus 5 into 2, that is nothing but UDL. Okay, so that will be nothing but 0 Newton. So this is how will be the shear force diagram. Let us draw this at this point only, that is shear force diagram here. Okay, shear force at A left was 0, shear force at A right was 30 kilonewton, shear force at D left was 20 kilonewton. There is a UDL, so that's why it will be an inclined line like this. Again there is a vertical load, so 10 kilonewton will be in shear force D left was 20 kilonewton, so this is 20 point, this is 30, this is 20. Okay, then shear force at D right is 10 kilonewton, so this is 10. Again shear force at B is 0, so that's why it will be again a straight line like this. Okay, so this is nothing but a shear force diagram for member AB. Now let us go for the calculation of shear force diagram of member BC. So this is BC, there is the vertical reaction, we know this is the 7 kilonewton force. Then again here the vertical reaction of 6 kilonewton. And these are the forces, 8 kilonewton and this is 5 kilonewton. This is point B, this is point C, this is point E, and this is point F. Okay, so like this, this is the shear force, this is the free body diagram. So shear force at B left is 0, shear force at B right is 7 kilonewton. So how to are the coin convention are like this, this will be considered as positive and this will be considered as negative. The force which are in left direction, the forces which are in upward direction, which will be considered as that will be considered as positive for this section. Okay, so shear force at B left means I take a section at the left side of this and I look in left direction, there are no any forces, there are not any forces, so that's why I have taken 0. When I consider shear force at B right, I consider section at this and I look in left direction. Okay, so there is a 7 kilonewton force, then I will consider it, so that's why it is 7 kilonewton and it is in left direction of this section and it is in upward direction, so that's why I have taken this positive. Okay, so this is the only difference is made by taking the section to the left and right of the point load. Actually taking section to the left and taking section to the right, it depends on whether there is a point load or not. If there is a point load, then you have to take the section, otherwise along the length you can continuously calculate this shear force diagram. Okay, now the shear force at E, when I say there is a point load, then I have to consider shear force at E left. Okay, so at shear force at E left will be 7 kN only. But when I consider shear force at E right, then I have to consider this 8 kN load. Okay, so 7, it is acting in a downward direction. I have taken this section at this right, I am looking in a left direction, so that's why it is in downward direction, so that's why the sign will be negative. So 7 minus 8 will be nothing but minus 1 kilonewton. Okay, shear force at F left, when I consider, it will be minus 1 kilonewton. When I consider shear force at F right, it will be minus 1 minus 5, that will be nothing but a minus 6 kilonewton. When I consider shear force at C left, okay, that will be also minus 6 kilonewton. When I consider shear force at C right, it will be again minus 6 plus 6 is equal to 0 kilonewton. Okay, so this is how we have to calculate the shear force diagram. So after this, depending on this, if I draw the shear force diagram, it will be like this: 0, 7 again positive. Okay, then after that it will be a straight line because there is a no load at 8 kilonewton load. Okay, it will be again minus 1. Again at it will up to 5 kilonewton, it will be a straight line. Again because of 5 kilonewton there will be again a drop, then it will be 6, and it again like this. So this is 7, this is 7, this is minus 1, this is also minus 1, this is minus 6, this is minus 6, and this is 0. So this will be nothing but a shear force diagram for this beam. Okay, so if we draw the shear force diagram for this structure, then it will be like this. Okay, so this is the portal frame. We are having this frame like this. Okay, so this is how this is nothing but A, this is point B, and this is point C. Okay, so this will be the shear force diagram for this frame. Okay, again there is still positive like this. There is a this is how will be the shear force diagram for this is denoted as positive. This is positive, this is negative. This is nothing but a SFD for this problem. Now we have to calculate the bending moment diagram. For that we will draw again this frame, and I will just show the reactions and loads on it. Okay, so this is the portal frame. We have reaction here like 7 kilonewton. Then after that there is a anti-clockwise movement which is equal to I think 60 kilonewton meter, and there is again horizontal reaction at this point. Let us show this side, which is equal to 30 kilonewton. Again there is a vertical reaction at this point C, that is equal to 6 kilonewton. Okay, so there will be the loads. This is 8 kilonewton I think, and this is 5 kilonewton. The distance are 2 meter, 2 meter. This is also 2 meter like this. Okay, again there is a UDL like 10 kilonewton per meter. Sorry, 5 kilonewton per meter. And there is again central point load. I think let us consider this at point this, that is 10 kilonewton. Okay, this is distance 2 meter, and this is also distance of 2 meter, isn't it? Like this. This was the structure. This is point A, this is point B, this is point C, this is point D, and this is point E, and this is point F, like this. So now bending moment calculation, BMD calculation. We have calculated the bending moment at point A. We know that is 60 kilonewton meter. So log this sign convention are considered as positive, this sign convention are considered as negative. Okay, so bending moment at A is known, and bending moment at point D, bending moment at point D, when we calculate, okay, so this is the moment there, that is in as anti-clockwise direction. So this is the, suppose this is the section, the moment is in anti-clockwise direction, then it will be considered has to be negative bending moment. So this is negative bending moment, anti-clockwise, and so that's why this is minus 60. Again we are taking the moment at this point. Okay, so minus 60 plus there is a load in, it will rotate in clockwise direction to the left, so that's why it will be positive plus 30 into 2. This one will again in anti-clockwise direction, so that's why again it will be in negative, that is 5 into 2 into 1. Like this bending moment at D has to be calculated. So how much it is? Nothing but okay. So it is nothing but a 10 kilonewton meter. Bending moment at point D is 10 kilonewton meter, and that is also negative. Well, at point B definitely there is not going to be any bending moment because it is an internal hinge. Okay, so at internal hinge there is a no bending moment resistance. Bending moment at A we got, bending moment D we got. Now bending moment at E we have to calculate. So bending moment at E is equal to, I'm considering the right of the section. Okay, I'm not going to consider this, I'm just going to consider the right of the section. Okay, so I have to use this sign convention, this one and this one. So this is 6 kilonewton load which is rotating in anti-clockwise direction, it will be considered as positive. So 6, because anti-clockwise in direction, in anti-clockwise direction it is considered to be positive. So positive 6 into 4. Okay, again 5 kilonewton load, it is in clockwise direction, right side of the section in a clockwise direction will be considered as negative, so that's why negative. So 5 into 2, like this we have to consider. So 24 minus 10, 24 minus 10, that is the amount of 14 kilonewton meter, that way the bending moment at this point E, and it will be positive. Now bending moment at point F, okay, only one load we have to consider, it is in anti-clockwise direction, that's why it will be again positive. 5 into 2, that is nothing but 10 kilonewton meter. Okay, so we got bending moment at A, we got bending moment at D, we got bending moment at E, and we got bending moment at F. As this support is roller support, definitely there is not going to be any bending moment. This is the internal hinge, so definitely their bending moment will be 0. And this is the fixed support, so that's why we got bending moment is equal to 60 kilonewton meter. So now we will draw the bending moment diagram. So this was the frame like this. Okay, so bending moment at this point was nothing but 60 kilonewton meter was negative. So consider this is positive, this is negative. So 60 kilonewton meter, then again 10 kilonewton meter, that point again there is a 0 kilonewton. So this is the nothing but a curvature. This is 2-degree parabola because there were, what we can say, there were UDL distributed all over the length. So that's why this bending moment is like this. Again, along the beam, the bending moment at point E was 14 kilonewton, so that was, it was positive. So yes, that was, this is the 14 kilonewton. then after there was 10 kilonewton load, so that's why 10 kilonewton bending moment at F was 10 kilonewtons, so that's why, and again 0. So like this it will be the bending moment diagram for this frame. This is nothing but BMD. Bending moment at point E is 14 kilonewton meter and bending moment at point F is 10 kilonewton meter. So this is how we have to draw the bending moment diagram. Actually it cannot be analyzed basically, but because of this provision of this internal hinge at point B, it can be analyzed by equation of a static equilibrium. Okay.